In econometrics, the generalized method of moments is a generic method for estimating parameters in statistical models. Usually it is applied in the context of semiparametric models, where the parameter of interest is finite-dimensional, whereas the full shape of the distribution function of the data may not be known, and therefore the maximum likelihood estimation is not applicable. The method requires that a certain number of moment conditions were specified for the model. These moment conditions are functions of the model parameters in the data, such that their expectation is zero at the true values of the parameters. The GMM method then minimizes a certain norm of the sample averages of the moment conditions. The GMM estimators are known to be consistent, asymptotically normal, and efficient in the class of all estimators that don't unregistered trademark T use any extra information aside from that contained in the moment conditions. GMM was developed by Lars Peter Hansen in 1982 as a generalization of the method of moments which was introduced by Carl Pearson in 1894. Hansen shared the 2013 Nobel Prize in Economics in part for this work. Description: suppose the available data consists of T observations at r a tar equals a 1 T, where each observation it is an n-dimensional multivariate random variable. We assume that the data come from a certain statistical model, defined up to an unknown parameter iai. The goal of the estimation problem is to find the a true value of this parameter, I0, or at least a reasonably close estimate. A general assumption of GMM is that the data be generated by a weakly stationary ergodic stochastic process variables. It is a special case of this condition. In order to apply GMM, we need to have moment conditions, that is, we need to know a vector-valued function g, y, I, such that where E denotes expectation, and it is a generic observation. Moreover, the function m, I, must differ from 0 for ia permil I0, or otherwise the parameter I will not be point-identified. The basic idea behind GMM is to replace the theoretical expected value E, A with its empirical analog a sample average, and then to minimize the norm of this expression with respect to I. The minimizing value of I is our estimate for I0. By the law of large numbers, for large values of t, and thus we expect that the generalized method of moments looks for a number which would make as close to 0 as possible. Mathematically, this is equivalent to minimizing a certain norm of. The properties of the resulting estimator will depend on the particular choice of the norm function, and therefore the theory of GMM considers an entire family of norms, defined as where W is a positive definite weighting matrix, and μ² denotes transposition. In practice, the weighting matrix W is computed based on the available dataset, which will be denoted as. Thus, the GMM estimator can be written as. Under suitable conditions, this estimator is consistent, asymptotically normal, and with right choice of weighting matrix also asymptotically efficient. Properties: consistency. Consistency is a statistical property of an estimator stating that, having a sufficient number of observations, the estimator will get arbitrarily close to the true value of parameter. See convergence in probability. Necessary and sufficient conditions for a GMM estimator to be consistent are as follows, where W is a positive semi-definite matrix, only for the set of possible parameters is compact, A is continuous at each I with probability 1. The second condition here is often particularly hard to verify. There exist simpler necessary but not sufficient conditions, which may be used to detect non-identification problem, order condition. The dimension of moment function m, I, should be at least as large as the dimension of parameter vector I. Local identification. If g, y, I, is continuously differentiable in a neighborhood of, then matrix must have full column rank. In practice, applied econometricians often simply assume that global identification holds, without actually proving it. Asymptotic normality. Asymptotic normality is a useful property, as it allows us to construct confidence bands for the estimator, and conduct different tests. Before we can make a statement about the asymptotic distribution of the GMM estimator, we need to define two auxiliary matrices. then under conditions 1-6 listed below, the GMM estimator will be asymptotically normal with limiting distribution. See convergence in distribution. Conditions is consistent, the set of possible parameters is compact, is continuously differentiable in some neighborhood n of with probability 1. The matrix is non-singular. Efficiency. So far we have said nothing about the choice of matrix W, except that it must be positive semi-definite. In fact, any such matrix will produce a consistent and asymptotically normal GMM estimator, the only difference will be in the asymptotic variance of that estimator. It can be shown that taking will result in the most efficient estimator in the class of all asymptotically normal estimators. Efficiency in this case means that such an estimator will have the smallest possible variance. In this case, the formula for the asymptotic distribution of the GMM estimator simplifies to. The proof that such a choice of weighting matrix is indeed optimal is often adopted with slight modifications when establishing efficiency of other estimators. As a rule of thumb, a weighting matrix is optimal whenever it makes the A-OE sandwich formula for variance collapse into a simpler expression. Implementation. One difficulty with implementing the outlined method is that we cannot take W equals IV1 because, by the definition of matrix I copyright, we need to know the value of I0 in order to compute this matrix, and I0 is precisely the quantity we don't unregistered trademark T know and are trying to estimate in the first place. Several approaches exist to deal with this issue, the first one being the most popular. Another important issue in implementation of minimization procedure is that the function is supposed to search through parameter space I and find the value of I which minimizes the objective function. No generic recommendation for such procedure exists, it is a subject of its own field, numerical optimization. J-test, when the number of moment conditions is greater than the dimension of the parameter vector I, the model is said to be over-identified. Over-identification allows us to check whether the model's moment conditions match the data well or not. Conceptually, we can check whether is sufficiently close to zero to suggest that the model fits the data well. The GMM method has then replaced the problem of solving the equation, which chooses to match the restrictions exactly, by a minimization calculation. The minimization can always be conducted even when no exists such that. This is what J-test does. The J-test is also called a test for over-identifying restrictions. Formally, we consider two hypotheses, A and A. Under hypothesis, the following so-called J statistic is asymptotically chi-squared with K-L degrees of freedom. Define J to be, and under, where is the GMM estimator of the parameter, K is the number of moment conditions, and L is the number of estimated parameters. Matrix must converge in probability to the efficient weighting matrix. Under the alternative hypothesis, the J statistic is asymptotically unbounded, and under, to conduct the test we compute the value of J from the data. It is a non-negative number. We compare it with the 0.95 quantile of the distribution, is rejected at 95% confidence level if, cannot be rejected at 95% confidence level if, scope. Many other popular estimation techniques can be cast in terms of GMM optimization. Implementations, our programming Wikibook, Method of Moments a starter, eViews, see also, Method of Maximum Likelihood, Generalized Empirical Likelihood, References.